Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next MIPS lecturette in ECPE 170 Computer Systems and Networks. In my previous lecturette, I introduced you to basics of functions in MIPS assembly. We discussed how to use the A registers A0 to A3 to pass arguments to the callee, the function that needs to be called. We saw how to use the JAL instruction to call a particular function. Then we saw the use of v registers to return values from these functions, and then we also saw how to use the JR instruction to return from the functions. In my previous lecturette, I discussed a handwritten solution for this particular C code right here. What I'm going to do is I'm going to show you a proper typed solution in my next line. You can go through it and convince yourself that it is indeed the correct solution. And also I would like for you guys to focus on the function related aspects of this code. So please pause your video and have a look at this code. Once you're ready, you can unpause and we can look into the function related aspects of this code. Okay, so let's focus on function related aspects of the code. Whenever a function is called with some arguments, we use the A registers in MIPS. So in this case, we use the A0 register to pass this argument as 0 to this function fun. Further assume that let's say the instruction that is in JAL fun is at address 50. Let's say that JAL fun is at address 50. The address of the next instruction will be 54. And further assume that the starting address of this function, where the first instruction is for that function, is 120. When we perform JAL fun, JAL stands for jump and link. So we are going to jump to that function and perform some linking. The linking happens under the hood. Specifically, when we perform JAL fun, the address of the next instruction, 54 in this case, will be stored in the RA register. So this is the linking part. Next, the program counter is going to jump to that function location. So now the program counter is going to hold the address 120. So the execution will start from 120 onwards. All of these instructions will be executed in a sequential manner unless a branching statement is encountered. In this case, there is no branching statement. Now recall that function was returning a value, so we are going to use the V0 register to return the value. Once the return value is set, now it is safe to return from this function, and we return from this function using this instruction JRRA. JR stands for jump register. So whatever contents are present in the RA register, that will be put in the program counter PC. So now the program counter is going to store the value 54, which is the address of next instruction that needs to be executed. So essentially we have returned from that function call, and now my execution can start proceeding normally from here onwards. So that's a recap of what we have seen in our previous lecturette with respect to functions. We saw how to use the argument registers A0 to A3. We saw how to use the JAL instruction. We saw how to use the V registers to pass the return value. And we saw how to use the JR instruction to return explicitly from a given function. The functions that we have discussed so far in the previous example, they were quite simple. They were not performing a whole lot of operation. For example, main was quite simplistic. It was just setting value of x, and then it was just calling a function that performed a very simple arithmetic operation. But in real life, and the programs that you're going to be developing for labs 11 and 12, they are going to be much more complex, where you'll be writing functions that will be performing much more significant amount of operations. Let's say that your main is already performing some crazy deal of computations using these registers S0 to S7. Furthermore, assume that main calls another helper function called func1, and that also needs to perform significant amount of computations. That func1 needs registers to perform those operations. Always remember, all the operations will be performed using registers. All the operations will be performed using registers. So func1 also needs those registers. It also needs those registers. It may possibly use S0 and S7 register that have already been used by main, but while doing so, it is going to overwrite the work of main, thereby breaking the logic of your code. So that's a bad thing that may happen if a function is allowed to unscrupulously change the values of some other functions registers. That's not nice. There's another potential problem that can arise in programs that have a chain of function calls. For example, let's say that I have a main function. It calls another function, let's say func1, and then func1 calls func2. In MIPS, when main calls func1, the return address is going to be stored in the array register. The return address is going to be stored in the array register. Next, when func1 calls func2, the return address still needs to be stored in the array register, and while doing so, we may have potentially overwritten the previous return address. So now your program will be in a limbo. Therefore, we also need to find a mechanism to save the array registers, particularly in those cases when you have a chain of function calls. So we need to safeguard our S registers and other temporary registers that are being currently used by a given function, and we need to somehow safeguard the array register. As it turns out, stack is an excellent data structure to save these registers, essentially saving the context of your program when it performs multiple function calls. So let's take a look into the stack data structure. I think it is advisable for us to recap base offset addressing mode one more time and understand how it essentially works, because the stack will be explicitly managed using base offset addressing mode. You have been using base offset addressing mode in C programs whenever you had a statement something like this: array of 5 is equal to 25. Here, array is the base address and 5 is the offset. Now the compiler is nice for us to multiply this offset with the size of the data type. For if it is an integer array, well, it is an integer array, so it would multiply 5 with 4, giving you a 20. Then 20 will be added to the base address, giving you the address of the target location where you explicitly put this value 25. In MIPS, base offset addressing mode takes the following form. You are going to use a register that stores the address of array. You would typically use an instruction like LA, load address, to get the address of the array. So S0 is going to hold the starting address. The address of the array will be specified inside of this register, which will be encapsulated in this parentheses here. And then the offset will be specified outside of this parentheses in bytes. This is going to be a constant number. So in this case, since each integer or each word is 4 bytes, I'll multiply 5 with 4, giving me a 20. So 20 is my proper offset in bytes, and S0 holds the base address. In this way, I'm going to access the target location, array of 5. So that's a brief recap of how base offset addressing methodology works, because it is going to be really critical for you when you manipulate stacks for your functions. So let's take a look into what stack actually is. You must have come across stack data structure in your courses like Comp 53. The element that goes in last is usually the first one to come out. In MIPS, we are going to handle stack memory space using a special register called the stack pointer, $SP. We will be explicitly using the stack pointer to manipulate our stacks. Typically, the stack pointer initially holds a very large address value, and as we start using the stacks, we need to decrement the stack pointer so that it may move downwards, and we will keep placing the values inside of the stack space. And when we want to retrieve the values, we'll read off from these memory locations and increase the value of the stack pointer so that it goes up, up, and up back to its original location. So let's take a look into an example where I want to push two values, 4 to the stack and 5 to the stack. Then I'll pop 5 next and then pop 4, because that's how stack works. The element that goes in last is the first one to come out. In order to push a value into the stack, first I need to adjust the stack pointer. Now, because we are working with MIPS 32 and we are going to be storing 4-byte registers into the stack space, we will adjust the stack pointer by 4. Essentially, we'll decrement stack pointer by 4 so that it arrives at a proper location where we can put a value. So initially the stack pointer was here, so we decremented by 4. So now the stack pointer is pointing to the location where the value can be put. I can now use base offset addressing mode to put the value 4 here. So 4 is pushed onto the stack. Next, when I have to push 5 onto the stack, I'll adjust the stack pointer one more time. So I'll decrement the stack pointer by 4 and push the value 5 there using base offset addressing mode. Pop operation is a complementary operation to push. So those of you that have taken electric circuits, you may know what complementary means, and so on and so forth. For example, the complementary of a resistor is a conductor. So here, the complementary of the push operation is the pop operation, so it has to go the opposite way. So in order to pop a value, first we read from the stack. We read from the stack using base offset addressing mode, and then we adjust the stack pointer. When we were performing the push operation, we were decrementing the stack pointer by 4. In this case, we'll increment it by 4 so that stack pointer moves up. Now to pop the value 4, first we'll read off from the stack first and then readjust the stack pointer so that it returns back to the original location. Always remember, guys, the stack pointer has to return to a proper place or its initial place where it started off for a proper normal program execution. If you find that your stack pointer is not at the place where it started originally, then that means something has gotten wrong in your program and you have to check your pushing and popping operations. So as a recap, in order to push a value into the stack, first you adjust the stack pointer, make it go down by subtracting 4 from it, and then you push a value there or you store a value there using base offset addressing methodology. If you have to retrieve a value from a stack, if you have to pop a value from a stack, you go the opposite way. You go the complementary of push operation, meaning first you read off from the stack using load word instruction, and then you adjust your stack pointer to make it go up by adding the value 4 to it. So that's the summary of stack operation. Now here's what I would like for you guys to do. Take some time here, pause the video and try to write a set of commands for pushing and popping values into a register, or rather for pushing and popping values into a stack. Specifically, you would like to push the register S0 first, and then after some time, you're going to pop it back. So please pause your code here and try to use base offset addressing methodology to push a value onto the stack. Your SP holds the address of the stack location. So SP holds the address of the stack location where the value needs to be put. All right, guys, I hope you had enough chance to attack this problem. Let me give you a solution to this. This is how you're going to push and pop values onto the stack. So here I'm pushing S0 onto the stack. So notice, first I'm adjusting the stack pointer. I'm making the stack pointer go down. That's always going to be the first step that you'll be performing. You'll subtract 4 from the stack pointer. Next, I store that word S0 using the base offset addressing mode. So SP holds the address of the location where the value has to be put. Since I am at the target location, I'll use the offset 0, a constant offset 0, to place S0 there. And then now, because S0 has been backed up onto the stack, I can do all kinds of crazy things with S0 in this section of the code. Once I'm done, I need to now retrieve the original value of S0 back. So I will pop S0 off the stack. Now remember, pop is opposite of push operation. In push, you stored the word S0 onto the stack last. In pop, you read it off first. So first I'm going to read the stack value and load it into S0. So load word $S0 $0 $SP. So I'll use my base offset addressing method. So essentially I have popped the value, and then I'll adjust the stack pointer, make it go up, as opposed to making it go down when you are pushing the value. So pause your video here. Please pay careful attention to these 4 highlighted lines. For push, first you adjust the stack pointer, then you place a value. For pop, first you retrieve a value and then adjust the stack pointer. one important thing to note here is that you are not destroying the values from the stack. You're not doing that as to what that my previous illustration was actually showing you. When you push values onto the stack, you are just reading them off. They are still there. So if I were to like push 5 first, then 4, then 6, and then when I read them off, I'm just reading these values off. These values will still be present onto the stack. So when we perform a pop operation, remember, we are not destroying the value that is present at that stack location. We are just reading it off. All LW does is it just reads the value off, and that's it. So this is how you are going to save context of registers, essentially stash them into the stack space in order for you to use them without any hesitation inside of your functions here. Okay. When you perform function calls in MIPS assembly or in any other programming language, there are usually two parties involved. The first is the function that is calling another function. So let's call it the caller. So the function that calls another function is called the caller, and the function that is being called is called the callee. Now both caller and callee have certain roles to play here with respect to operating the stacks. So let's take a look into what the caller should do with the stacks in addition to performing its regular operations like saving the arguments in A0 registers and jalling to a particular function or jal to a particular function. So let's talk about what a caller must do with the stack prior to function call. And it is going to be a little bit less common for our programs because caller usually does not have to do crazy deal of operations with the stack unless it satisfies certain conditions. And here are those conditions. A caller must use the stack if it is using one of the temporary registers, T0 to T9. If it is using one of these temporary registers, it's better for the caller to stash them onto the stack, to push them onto the stack so that they are available for the function that it is calling. So that T0 and T9 are available for the function, for the callee function. If your current caller is already working with its own arguments, and let's say that it needs to pass arguments to its callee, then it needs to definitely stash A0 to A3 onto the stack. Therefore, stack space is really very important for the caller if it is passing arguments to another function while at the same time it is also using its own arguments for its own operation. It needs to use stacks then. There's one more time when caller uses stacks, and that is when it wants to pass more than 4 arguments to the callee. So we use A0 to A3 registers, A0, A1, A2, and A3, the 4 registers to pass arguments. But for some reason, let's say that the caller needs to pass more than 4 arguments, it can use the stack space. But it is not necessary for our programs. I can assure you that our programs can be written in such a way that functions need no more than 4 arguments. So these are the times when a caller needs to operate or needs to use the stack. When it needs to save the temporary registers T0 to T9, or or if it requires to save the argument registers A0 to A3, its own argument registers. Callee has much more significant role to play with respect to stack. In fact, it is going to be required for our programs. What we are going to do is have our callee push the S registers that are being used by the caller onto the stack. All right, whatever S registers the caller for a given function is using, we need to save them onto the stack. So if function 1 calls function 2, function 2 should save S registers that are being used by func1. So that should happen. It should also push the array register onto the stack, because let's say if this function were to call another function, the previous return address will be overwritten. That needs to be saved. So if main calls func1 and func1 calls func2, func1 needs to save the array register so that it knows, or rather your program knows, from where to return to after func1 is done. Then the callee can do its own function stuff, and next, prior to return, just before returning, just before executing j.r.r, it's going to pop RA first, and then it's going to pop the S registers in the opposite manner. So remember guys, pop operation is complementary. It's the opposite operation of a push. So the order in which you push the registers, you will use the opposite order to pop those off the stack. So you push S registers first, then you push RA, do the function stuff. Now the pop is going to be opposite. You pop RA first because it was pushed the last, and then you pop the S registers in the opposite order that you pushed initially. Once this is done, it is safe to return from this function, so you will execute j.r.r as your sixth step. So your sixth step will be j.r.r right here. Now some word of caution here, or rather some words of wisdom here. Do not haphazardly use your temporary registers and your general purpose registers. Use them in a very specific order. They are labeled as S0 to S7 for a reason. They are labeled as S0 to S7 for a reason, so that you will use S1 first, then S2, S1 next. My apologies, you'll use S0 first, then S1 next, then S2, and then so on and so forth. If you were to use a haphazard, or if you were to use these registers in a haphazard manner, then you will be really confused with respect to which registers need to be pushed. That's a very tricky thing to handle, and that can quickly result in incorrect programs. So please make sure that you use S0 register first, then S1, then S2, so that you have a nice order of pushing these registers. So for example, if I use S0, S1, and S2 in my caller function, I'll push them one by one, and then in the end, I'm going to pop them in the opposite order. That's so nice. That gives me such a good structure for my program. Instead of pushing like S7, then S4, then S3, then popping S3, then S4, then S7. That's very unwieldy way of using the registers. Okay, so let's summarize what the caller needs to do and what callee needs to do whenever we perform function calls. As far as the caller is concerned, there's no major tasks that are going on except for saving one of the T registers that it is also using, or several of the T registers that it is already using, and or saving the argument registers. So typically when I write programs, I work with nice stub for caller and callee. So my caller portion looks something like this right when it is about to call a given function. So I'll put nice comments like save T registers if used, save A registers if used, JAL to function, and then I'll put a comment, retrieve A registers in opposite order of pushing, and then finally retrieve T registers in the opposite order. So I would write these nice comments in my caller portion whenever it is about to call a particular function. There's one more aspect that I missed here, and that is after saving the A registers, now is the time to prep arguments using A registers. So if this caller is already working with its own set of A registers, it's going to first save them, and then it is going to prepare arguments for this function. Then it is going to JAL to this function, and then once the program returns from that function, the caller is going to retrieve A registers in the opposite order, thereby regaining its own argument values, and then it is going to retrieve the T registers. So that's those are the tasks or responsibilities of a caller. The callee's responsibilities are to be carefully noted. It is going to be a required portion in your MIPS code that you make sure that you save the context, you save the S registers and RA register onto the stack. So here's how a caller, or rather callee, going to look like. So callee is going to be the function. Callee here is just a label. You can put whatever label that your program requires it to put. I can have like function or func1, func2, func3 as my label for this function. Usually I put nice comments to guide me what I need to do with the Callee. So I would do something like this: save S registers that, or save S registers used by this function's caller. So I'm going to save those as registers and then save array. Always save array. That's my advice to you. Always save array register onto the stack. Then here we'll do some function stuff. And then prior to return, here's what we are going to do. We are going to, if this function is going to return value, we are going to place return values in V registers. Then we are going to pop array, and then we are going to pop S registers in opposite manner. We are going to pop those S registers. We are going to retrieve those S registers in the opposite manner. And then finally, we are safe to return back from this function. So JR array. So you can use these two as quote unquote stub for functions in your C programs, in your MIPS programs. Make sure to use these comments, and please pay careful attention to these comments. All right, now before I end this lecturette, let me show you how I'm going to modify the problem 1 to use the stack. If you notice, this is the program that I showed you. The main function, the caller, was already using S0 and S1 register here. It was not using any of the T registers. Neither was it using any of the A registers as arguments. So I did not have to save the T registers and A registers onto the stack. I could just prepare my arguments and I could just JAL to that function and move on with my regular main operation. The Callee, however, it definitely needs to save the S registers onto the stack, the S registers used by its caller. So main was using S0 and S1. So this function is going to store S0 and S1 onto the stack. Notice how the pushing operation is being performed. First, I adjust the stack pointer. Then I store our value onto the stack using base offset addressing methodology. In order to save S1, I again adjust the stack pointer and then save my register. Then I do my function stuff. Now if you notice here, I'm free to use S0 and S1 registers because S1 and S0 registers of the main have already been stashed onto the stack. So I'm free to use them here. So I use them freely here. I set my return argument. Prior to return, I'm going to pop the values in the opposite order. I pushed S0 first and then S1. So I'm going to retrieve S1 first, then S0. So I first read from the stack and then I adjust the stack pointer. I read S0 from the stack and then I adjust the stack pointer. Please make sure to perform equal number of pushes and pop operations inside of your functions. Only then will your stack pointer be at its proper location where it needs to be. A mismatch in the number of push and pop operations may potentially break down your program. So now that the context has been retrieved, now that the values that were used by the main function have been retrieved, it's safe to return back to the caller. So I perform JR array. So that's how you are going to use the stack space for your programs in Lab 11 and in Lab 12. I hope you enjoyed this lecturette. I hope you understood how to use the stack space. I hope the base plus offset addressing methodology is ingrained in your programming toolbox well. I'm going to end my lecturette right here. In my next lecturette, I'm going to give you a complete solution to this particular C program here using QtSpim. I will not be using a pre-written solution to perform this coding. Instead, I'll be performing live coding so that I am open to make mistakes. Should I make any mistake, please note it on YouTube video, on YouTube channel. Should I make a mistake, I'm going to show you how those mistakes can be alleviated as well. I think it's a good time to stop this lecture right here.